Okay, our last speaker is going to give us a talk on data-driven inference and porous media flow.
This research is actually part of the things I do in my spare time when I'm running my company as a CEO. So I'm going to be basically trying to connect physics with data-driven processes. And my view is going to be specifically oriented in the resource simulation realm. So let me give you some motivation, okay? So as you maybe know, many in the oil and gas industry, many people are interested in solving larger and larger problems. Despite how many computing resources they may have access, they would like always to solve the largest problem possible with all the physics that you can fit in. On the top of that, and we are talking about problems that are in the order of 10 to the 8 grid cells. And on the top of that, they would like to take decisions based on those simulations. So they are basically, this entails running optimization problems several thousands of times using these models. And if additionally they want to assess uncertainty, then that adds another order of magnitude into this computational setting. So there is enough justification to find alternative ways to mitigate the computational cost of these processes. So I'm going to give you my view about how I see this possible merge of data-driven processes and physics. So we have latest technologies in big data, machine learning, and pushing the MLO, the multiple science. So we are capable of dealing with big complex problems. And the main motivation is we want to improve performance. That's basically the main motivation. And this has been a recurrent need for many years in the oil and gas industry. So we talk about surrogates, proxies, and so on, reduce all the models to be able to cope with the computational costs of these models. So the outcome is to get these simplified models, but still retain part of that physics. But the latest trend is why don't we use this amount of data, the additional data we're getting from the field, and data that we can actually recycle from simulations to try to gain more insights. So why don't we try to discover other things that we don't know? And this is when we are going to have possibilities to improve our understanding of our physical models. Start discovering what we don't know. And when we basically merge these two needs, we're going to be coming up with hybrid models. Models that are going to have a minimal physical structure to be able to capture the main trends, but additionally, going to be able to consume, digest all the additional data that we have in the field. Moreover, if we can do this, basically, we're going to be able to rationalize how we're getting this big data in our fields. Because if we have more understanding, we have better models, we're going to understand better how to acquire this data, when and where, and how. So the agenda of this talk is going to consist of these simple items. So I'm going to give you a glimpse of a data-driven inference framework I'm working on, and then how this framework is composed of these two elements, CNN, convolutional neural networks to infer states in the dynamical system, and LSTM to infer responses, outputs, production outputs in our case. And then I show some computational results and final remarks. So let me give you a little bit of history about what is the role of data-driven methods in oil and gas. We can date these efforts from the 1990s, I will say. Oh, sorry. Oh, this is, OK. So I'm just comparing what is going on in the AI. We know that artificial intelligence has been basically an active field since the 1950s. I just highlighting from the 1990s to nowadays. In oil and gas, I was the first paper that had a title related to artificial intelligence was 1969. Imagine that. And in 1990, people started getting quite interested in neural networks, not in the way we know them today, of course, and they started exploring other topics like support vector machines, and another field that basically pushed a lot of things in data-driven processes was the creation of reduced order models. The reduced order models, it typically entails to know part of the physics, so you try to create some sort of white box or gray box to reproduce what's the physics, the original physics of the system. And then there's a bunch of other efforts that have been taking place in oil and gas that has been somehow inspired by what is going on in the general literature of artificial intelligence. I will say in general, the perception is there's more things going on in your science than the rest of engineering, perhaps because your physicists are more daring in trying new things. But I'm trying to do my piece in the side of rest of engineering, and I believe there's a lot of huge opportunities to basically try to bring all these technologies in our business. So as I mentioned before, our interest is try to reproduce or mimic somehow, capture the dynamical system that is entailed in our case by reservoir simulation systems. So we have an equation that basically, this thing is, okay. It's very sensitive. That's what I'm noticing. Okay. Yeah. Okay. So we have the equation that relates states, let's say pressures, new saturations, new stresses, from input parameters or control parameters. We have the second equation basically relates those states with outputs, production profiles, water cuts, and so on. So the way we're going to state this, we're going to take any instance of the state space and map it through the use of a convolutional neural network to a future state. Now, notice I'm saying pseudo state. So now I'm going to assume, as in the case of reduced order models, I'm going to be capturing every snapshot in time. So my motivation is, if I don't have all those snapshots, I would like to know if I see a frame, like in a movie. When I see a frame or a sneak preview of a movie, I know the whole movie. I can infer the movie. So I would like just to, using some physical knowledge about the process, capture that snapshot somehow, indirectly, and map that from the final state. Let's say 10 years of simulation, 20 years of simulation, and so on. And once I have those states, I would like to map those states into outputs. Okay? Simple. And for that, I'm going to use a long, short-term memory recurrent neural network. So the way we're going to be mapping, in the case of the CNN, we're going to come up with some pseudo state or some current state to map images onto images. So we're going to use this convolutional encoder-decoder that we're basically going to bring this representation to a small dimensional space, and from there map into the target image, or target pressure field or saturation field. So let me give you a motivation about this. And this is where I'm spending some of my research, how we could basically relate convolutional neural networks with other things that have been also emerging lately in the literature of dynamical systems. And the reason is the following. When we use convolutional networks, we're trying to see if it's possible to interpret what is going on in the physics of the process, which is not straightforward. But when you use POD, this is our old technology, we can basically, through modes or eigenvectors, we can kind of track what is really going on in terms of the resolution of my solution at any given time. DMD, which stands for dynamical mode decomposition, has been an alternative method that has been gaining a lot of traction in the last 2 or 3 years And it's very powerful because it retains part of the coherence, spatial-temporal coherence associated to these fields. So you can see, basically, I just showing 4 modes, the first 4 modes. DMD does a better job than POD. Basically, with just 1 mode, I can capture, in this particular example, very well the dynamics of the saturation field. When I use CNN, well, it's less clear what is really going on. When I try to display the activation function associated to this problem. But there is something there, nevertheless. There is something there seems to be reflected in those different activation functions I pull out from the first convolutional layer from my CNN. So in terms of the recurrent neural network, I guess most of you are familiar. So the recurrent neural network basically takes output or some middle layer, so outputs of those layers into a previous layer. And just trying to have some sense of recurrence. But the problem with these particular implementations is we have the problem of vanishing gradients. So if you have a lot of layers, the gradients that we use to estimate the function, when we do backpropagation, start tending to 0. Because it's like we have a chain rule. So if we have small changes, all this chain rule vanishes. So we lost track what was happening before. So as an alternative, LSTM has been proposed. So you can think of LSTM as a neural network where each node has a little neural network that has the capability to retain, has some memory to retain past events. So an example. This is a case of drilling. So just comparing a standard recurrent neural network with LSTM. You can see here a torque anomaly indicator. You can see that the resolution for the LSTM in this case is superior to RNN, a standard RNN. You can see RNN is kind of delaying the response. And this is actually has been referred in the literature many times. So let me give you an example. This is a small case, but it represents a lot of combinations. That the problem here is, okay, let's infer what will be the pressure field if I take 5 wells, 1 producer, 4 injectors, move them around arbitrarily, use for these 5,000 combinations. We know that there's a huge number of combinations, and see if I can infer what will be the pressure field for a given combination that I haven't seen. So, and for this, what I'm going to do, so you will ask, okay, so you have 5 wells. Each well has this is a 2D problem, an XY position, right? So you have to map that XY position into a pressure field. So it's basically a scalar into an image. So how do I jump from there to the pressure field? And here comes the idea, okay, let's come up with some pseudo pressure field. And you can use multiple rows for that. You can solve an upscale problem, much smaller problem. You could solve a steady state problem associated with those positions. Or even much simpler than that, you could use some kind of radial basis functions that you will develop around the points where you believe the wells are. As simple as that. And using some proposition principle, you kind of approximate a pressure field, given that this is a diffusion problem, right? So that's what we did. Take the pseudo pressure and map it into a real pressure field. And then regarding the responses, we just map those pressure fields into the production profiles using LSTM. So here are your results. This is the reference. This is the predicted pressure field, okay? And this is the relative error, the difference between these two. Okay? So you can see that it's quite small. And this was more or less all the way. And using just 4,000 samples for training, 1,000 for testing. Regarding the pressure, the production, we did also a good job. Not as good as in the pressure, I would say, relatively to the pressure field, but still is in the ballpark. So inferring production from just positions from basically a very simple argument on how the pressure field may look like for those pseudo pressure is quite impressive, because I'm not using a very large number of samples, given that we know in deep learning it's recommended to use a large number of samples. This is another case, more in the realm of unconventionals. So it's a fracture system, 2D. Here we use even a smaller number of samples, just 1,000. We're going to use 800 for training, 200 for testing. And the question here is, can we infer different number of fractures, fracture length, and permeability? So as you can see, number of fractures is basically a integer number. Permeability stands for the uncertainty of my system, and the fracture length is a real number. Okay? So we use Latin hypercube to do the sampling, and then we use 800 for training. And this is more or less, this is a reference case. Okay, for this is having 4 fractures on each side of the well. And this is with more fractures, and basically capture the trend. Perhaps a little bit behind, I would say, because the pressure in the prediction case is not as developed as in the reference case. But we did a much better job in the production side. So my message here is, okay, so we use certain physical understanding of the problem, okay, to reduce the number of samples. So I can afford, of course, my description of the neural network, of the deep neural network, was very simple, given the small number of cases. But I took advantage of the physics of the problem to be able to do this. So results are encouraging, despite the limited use of data. Using physics knowledge is key to generate efficient data-driven models. That's why, trying to automize the way we do machine learning could be challenging if we don't use certain knowledge about the physics of the problem. Infer flow dynamics from additional data. And this is the other thing why I think there's a big promise on this. When we use reservoir simulation systems, we take a lot of assumptions to be able to represent a particular physics. And we know what are the set of inputs that those models take. We're confined there. But now that we have the possibility to gather all sorts of data simultaneously, time-dependent, real-time, coming from your physical acquisition, from logs, from drilling, from completion, there must be ways to map all that information directly into production. Okay? And not just be constrained to the assumptions that simulator takes. Look at our state variables, saturation, stresses, and explore. And this is very important, and very important for the oil and gas industry. Try to retrieve interpretation from these models. And that's why you cannot just strictly do it using a data-driven model, because you're gonna have no strong arguments to say, okay, there is some trend or there is some physics that is captured through this model. So interpretability is very important. If you want to convince oil and gas industry specialists, those models have to have interpretability. And that's what I'm trying to convey when I basically look at these methods are used in like DMD, like POD, try to see if there are ways to map those interpretations into deep neural networks. Thank you.
Thank you. We have time for a question or two, although the reception starts about right now. So we'll try to keep it quick.
Just really quick. So in your production prediction, can you go back to that slide? So that's using public data, right? It's monthly. I'm sure that that's your cumulative oil production.
Yes, monthly. This one or the other one?
This one, yes. So it's monthly. You're using the public data for this one. You're using the public data for this.
Public?
One. Public data.
No, this is simulation data.
Oh.
I haven't used. Yeah, this is simulation data.
Okay, thank you.
Just verifying my results.
Last question.
I wasn't clear on your use of pseudo data or
Pseudo pressure.
Yeah.
Pseudo pressure field.
Yeah. What was it that you used for pseudo pressure field? What type of data?
Okay, for the case of the well placement,
Yeah.
I know the position of the wells. So I have a description of the XY coordinates. So
Just the position.
just a position.
And-
I mean, but you need to represent this into some sort of map, because I'm mapping
Okay.
an image onto an image.
So map back to first principles, you're saying?
No, take the positions and reproduce using radial basis functions, like you will do in kriging, how the pressure field displays
Yeah.
In-
Sort of the nominal.
in a kind of a steady state fashion.
Okay.
And
Thank you.
from there, you map it to a real pressure field.
Thank you very much. Let's thank all the speakers.